Okay, in this video I'm going to illustrate how to use LISREL SIMPLIS syntax in order to test both a regression model and a path analysis model. So basically the data for these two models is basically provided right here in this SPSS file. I have data on 100 cases with 6 variables. I have subject matter interest, intrinsic motivation, anxiety, cognitive engagement, work avoidance, and achievement. So basically there are a couple of ways that you can input data into LISREL. One way is to utilize syntax and basically just simply type in the simplest commands and also whatever matrices that you're working with. Another strategy is to just import the data directly into a pre-processing program called PreLIS. And in that program you can do whatever types of data screening, dealing with missing data and so forth, and then that is basically utilized or input into LISREL, which is then used to test your models. But in this particular video I'm mainly going to be focusing on using syntax as a way of putting information into LISREL and running some models. So in this case, the first thing you want to do is to generate or is to open up the LISREL. So you go to SSI Incorporated. I've got the student version on this particular laptop. So when you open up, you can see that you've got now a blank screen. And so the first thing that I'm going to do is illustrate how to run just a multiple regression model using syntax. So the first thing you need to do is go to File and to New. And then since we're going to be using the simplest command language as opposed to LISREL command language, we're going to click on Simplest Project. You can double click on that, or click on it and then click on OK. And I'm just going to call this one, I'm just going to call it Multiple Regression 2. Because I already have one called multiple regression. So then you save. So you have to basically this leads to this page being opened up, and this is where you would type in your command language. So in the first line you generally type in a title. So I'm just going to call this multiple regression 2. So this is basically just the title line, and so you can just call it title, and there you go. The next step is to type in the observed variables. So I'm just going to type in observed variables, and this is a command, so this has to be there. So type in observed variables and then the variable name. So I'm just going to run a multiple regression with cognitive engagement and work avoidance as predictors of achievement. So I'm going to type in cog engage and work avoidance and achieve. And keep in mind that you can't have just a very long variable name. So hence I've kind of truncated everything so that it will run. So now the next step is to incorporate whatever matrix that you're working with. So I'm going to incorporate or type in a correlation matrix of the correlations among these 3 variables. So from my SPSS data file. So I'd already actually run the correlations among the variables. Here they are, and I've also asked for means and standard deviations. So at this point I will type in the correlation matrix. So basically you'll just type it in this particular format right here. So I've got you'll have ones along the principal diagonal. You'll have the correlation between your 2 variables, in this case engagement and work avoidance, which was negative 0.33. And then below you'll have the correlation between engagement and achievement was 0.42. And then between work avoidance and achievement was negative 0.34. And then I'll have another 1 on the principal diagonal. These they don't have to be necessarily nice and pretty, as you know, this is obviously a little it may look a little weird, but the program will run fine this way. If you want to you know, kind of straighten things up and make things look a little nicer, you can certainly do so. Just make sure that there's a space between your values. So anyway, there you go. So I've kind of cleaned things up a little bit just to make it look a little bit better. So the next step is to specify the command relationships. And so at this point, what you'll do is you will type in the name of an endogenous variable. And basically, an endogenous variable is one that is being whose variance is being predicted or accounted for by other variables in the statistical model. An exogenous variable has no predictors associated with it. So in a standard multiple regression model, basically the endogenous variable is nothing more than the dependent variable, and the exogenous variable would be nothing more than the independent variables. When you run into path analysis with multiple variables, what you can have are multiple endogenous variables as well as multiple exogenous variables, and I'll illustrate that in a little bit. So in this case, I'm going to use achieve as my exogenous variable. That's my outcome variable, and I'm going to type in the basic form of the equation is achieve equals cog engage and work avoidance. So the next thing you want to make sure to do is to specify your sample size. So I'm going to type in sample size, and I had 100 in this particular data set. Typically, when you're running SEM models, the sample sizes are a lot larger than this, but this is just to illustrate the basics for carrying it out. So be sure that you specify that. If you are going to work with input data, as you see right here, and you're going to generate, say, a correlation matrix or a covariance matrix, you'll need to deal with the issue of missing data before you start inputting the correlation or covariance matrix into the program. So now I'm going to type in path diagram and then end of problem. Okay, so the method of estimation, by the way, in programs like LISREL and Amos and so forth, is the default method is maximum likelihood, and so there are ways of changing the syntax and allowing for different estimation approaches, but those are maximum likelihood is the default, and we're going to stick with that for this illustration. So then you highlight everything, and then up here where you've got the little guy running, just click on Run LISREL. And so here you have a basic multiple regression model. Now the thing is that because I've only input a correlation matrix and I don't have any information about standard deviations and so forth, then the solution is fully standardized, meaning that whether you know, typically if I have unstandardized if I were running this analysis with standard deviations or using a variance covariance matrix, then under the estimates tab right here, these would be reflecting unstandardized coefficients. But instead, because we only inputted a correlation matrix, these are fully standardized. So basically these are nothing more than beta weights. And then what you see right here is the zero order correlation between your two exogenous predictor variables. So you'll notice that if we click on standardized solution, nothing changes. And again, that's because no unstandardized estimates have been computed. If you look down a little bit further under t-values, this is basically these are these are t-values associated with your path coefficients or your regression coefficients in this case. So you have t-value at 3.7, negative 2.42, negative 3.13, and basically when you're assessing significance, you're looking for t-values that would be you know, above positive 1.96 or below negative 1.96. Those are conventional thresholds at an alpha level of 0.05. So at any rate, if you click on out of this and just go into the output box right here, output file, as you scroll down you can see this is just sort of a rehash of everything that we typed in previously. You'll see that you get the correlation matrix, and then you'll see that you've got the LISREL estimates. You've got the regression coefficients that were actually printed out in the previous figure. You have the standard errors, and then you have z-values, which again, you're basically using threshold. If you're adopting an alpha at 0.05 threshold, then you're looking for z-values that would be above 1.96 or below negative 1.96. And then you also have the p-values. You'll see here we also have the R-square value. This is the proportion of variation in achievement that is accounted for by cognitive engagement and work avoidance. You'll also notice down below that you've got goodness of fit statistics, and basically in a multiple regression model you have 0 degrees of freedom, and the model is called just identified. Basically there's nothing really to be gained by trying to assess goodness of fit, because the model is going to fit the data perfectly. And that doesn't mean that you prove in your model or demonstrated any kind of causal relationships. It just is a matter of fact that you have just enough information in your correlation matrix to uniquely estimate each of the parameters in your model. So really these are very uninformative in this particular context. It's really more informative when you have an over-identified model where you have degrees of freedom that are 1 or greater. So at any rate, so let's say I want to estimate the unstandardized solution as well. Well, I can certainly do this just by typing in standard deviations, and then just typing in the standard deviations for each of your variables. So cognitive engagement, the standard deviation was 79.5. For work avoidance, it was 58.5. And for achievement, it was 22.5. If I want to also estimate the intercept for the model, then I would also want to incorporate the means for these variables as well. So I can just type in means, and then I can type in, so the mean for cognitive engagement was 645, the mean for work avoidance was 490, and then the mean for achievement was 245. So now what I would do is to get the intercept, what I would need to do is just to type in CONST for constant, and there you go. So now when I highlight all this information and then click on Run LISREL, you'll see that I get my model again, and I can use this little drop down. So these are unstandardized regression coefficients that you see right here. So so basically we would say, well, for every 1 raw score unit on cognitive engagement, there's an increase of 0.1 raw score units on achievement. For work avoidance, for every 1 raw score unit on work avoidance, there's a decrease of 0.09 raw score units on achievement. Now what you have right here, this is the covariance between engagement and work avoidance. So and then what's these numbers out to the side, these are the variances of those variables. So in the model, we're estimating a variance of cognitive engagement, work avoidance, the covariance between them, and then the paths from each of our exogenous variables to achievement. And then also there's the prediction error. So this is the residual variation that is unexplained in achievement. If I want to look to see which of those coefficients are significant, I can look at t-values. And generally, if it's not significant, you'll see that the t-values will show up in red. So if that 1.96 threshold is not met, you'll see a path in red. In both of these cases, you can see that the paths are not red. You can see that really that all of the parameters in the model are statistically significant. So now I'm going to go back to the output file, and so now you can see we have the structural equations. Here's our intercept that we had asked for when we included the constant command. And then we have the regression coefficients for cognitive engagement. These are unstandardized now. For cognitive engagement, work avoidance, you have the standard errors for each of these as well as the z-values for each of those. And then you also have p-values that are printed out in order to test each of those coefficients. Again, you have the error variance that's listed as well as whether or not it's statistically significant. And then you have an R-square value. So you can see that really much of this is the same as what we had seen previously. So now kind of scrolling down again, our fit statistics, the degrees of freedom is 0. So basically that's why this says the model is saturated and the fit is perfect. Again, that doesn't mean that your model is an accurate representation of reality. It's just that the fit is perfect because you end up with a just identified model. And so it's only when you have an over-identified model that's really particularly useful. So that's sort of a quick overview of running multiple regression models using LISREL. Now let's try a different type of model. So in this case, what I'm going to do is I am going to click out of here, and I'm going to generate a path analysis. So in this case, I'm going to go to File, New, and under SIMPLIS project, I'm just going to call this Path Model, and click on Save. And now what I'll just do is I'll just call this Path Model. And in this particular case, I'm going to type in a variance covariance matrix. So in this case, I've just gone ahead and typed everything in. So you can see I've got a title line, observed variables. So I've got SMI, IM. So SMI is subject matter interest, IM is intrinsic motivation, anxiety, cognitive engagement, work avoidance, and achievement. Then I've got a covariance matrix, which I actually took from what I generated out of SPSS. So this is actually the variance covariance matrix. Basically, along the primary diagonal are variances, on the off diagonal are covariances. So so at any rate, like I said, you don't repeat everything above the primary diagonal. So as you can see, I tried to kind of straighten it out and make it look a little cleaner. I've got the means also for each of the variables as well listed. So that's subject matter interest. The variance is 5625. Its covariance with intrinsic motivation is 675. The mean for subject matter interest is 600. The mean for intrinsic motivation was 350, and so forth. I've also specified relationships here, and now I've got two endogenous variables. Actually, I've got three endogenous variables. I've got cognitive engagement being predicted by subject matter interest, intrinsic motivation, and anxiety. I have work avoidance being predicted by anxiety and subject matter interest, and I have achievement being predicted by cognitive engagement and work avoidance. The sample size is still 100, and then I also include path diagram and end of problem. I also, as a way of assessing possible areas of misspecification, you can also type in print residuals, and you can actually look at residual matrices as well in order to look at possible areas where the model is misspecified. So we're not going to really get too far into that on this particular video, but we are going to highlight everything and press run. And so here we have our path analysis. So as you can see, this is, basically these are containing our fit statistics. And generally, there are two levels in which you really kind of assess, or two broad levels in which you're assessing the fit of the statistical model. You're looking at overall model fit, and you utilize global fit statistics to do that. So one way in which you could assess overall fit is the chi-square test. So this is a significance test, and basically what you're looking for is a p-value that's indicating non-significance. So actually a non-significant chi-square test value is actually suggesting that you have good fit. So the chi-square is, you could kind of refer to it as sort of a badness of fit test. So if it's statistically significant, it would actually indicate that you have problems with your specifications in your model. Just keep in mind that because SEM is a large sample procedure, what can happen is that you can have a lot of, too much power, so to speak, and you could actually end up achieving statistical significance with a model that is actually fairly well specified. And by the same token, you can have, if you have a low sample size, such as in the case that we have in this data set, it may be underpowered. And so you may have really more severe lack of correct specification, and the p-value not be significant. So it's important that you kind of keep those issues in mind. So that's one of the reasons why it's kind of useful to look at different types of fit statistics. Another fit statistic is the root mean square error of approximation, which is also printed out right here. And so what you're looking for, evidence of a really close fit would be an RM-SEA value that's less than 0.05. And up to about 0.08 would be considered reasonably close approximation or reasonably close fit. So it actually turns out that based on this information right here, it looks like there's evidence that the way this model is specified, that there's a reasonable fit to the data. So we can also look at, if we go to estimates, I'm not a big fan of the drawing program here with LISREL, but you can sort of click on paths and you can kind of modify them and straighten things out a little bit. But you can see right here under estimates, these are basically unstandardized path coefficients. So they're interpreted pretty much the same way that you would interpret unstandardized regression coefficients. You can also see that these are the variances for each of your exogenous variables, and they're exogenous because they have no predictors in the model. These are endogenous variables over here because they have variables that are predicting those variables. So at any rate, you can see so you have error variances associated with each of these variables, or basically what's not being predicted by their predictors. You also have over here, these are all covariances among the exogenous variables. If you want to look at significance, you can go to t-values, and so you can see that with the t-values, here are a couple of examples. You've got the red t-value right here. So this intrinsic motivation predicting engagement. This would be significant for a one-tailed test, but not for a two-tailed test. And then you've got non-significant covariances among some of your variables, but the remaining paths all would be considered statistically significant using a two-tailed criterion. So we can also look at the output file, and so when we go to the output file, you can see that again, here's our syntax right here, and as we scroll down, you can see you've got your covariance matrix. You can see it's actually a little cleaner than what we had up above. You'll notice that you've got the equations. So you have cognitive engagement, being predicted by subject matter interest. You can see there's our z value and the p-value. So that was a statistically significant predictor, subject matter interest. And mind you, these are all unstandardized estimates. So these are interpreted like unstandardized regression coefficients in multiple regression. So you have a significant predictor in subject matter interest, significant positive predictor, a significant positive predictor of intrinsic motivation. Actually, let me kind of scratch that. If we're using a two-tailed criterion, it would not be significant. With a one-tailed test, if you're testing a directional hypothesis, the p-value would actually be half of that printed right here, so it would be about a 0.04. And then you also have anxiety. There's a negative predictive relationship between anxiety and cognitive engagement. And you can see that these three predictors explain roughly 29% of the variation in cognitive engagement. You have a negative predictive relationship between subject matter interest and work avoidance. That was statistically significant. You've got a positive predictive relationship with anxiety and work avoidance. That was significant. And you can see that those two variables combine to explain roughly 18% of the variation. And then achievement, you've got cognitive engagement being a positive predictor, work avoidance being negative. Both of those were statistically significant and accounting for about roughly 21% of the variation. So now we can look at global fit, and basically you can see that the degrees of freedom for our analysis was 5. So basically, if your degrees of freedom is 0, you have what's called a just identified model, and basically interpretation of the fit statistics is all going to say that you have a perfect fitting model, and it's wholly uninformative. It's not really any evidence that you've got correct specifications. It's just that's just kind of the way it is. If you have one or more degrees of freedom, then the model is called over-identified, and in that context, the goodness of fit statistics are useful for interpreting how well the model is fitting the data. If you have less than 0 degrees of freedom, you have what's called an under-identified model, and the model will not converge, and you won't get all the nice fit statistics and so forth. You'll just get an error message. So at any rate, in our current case, we have an over-identified model, and so several pieces of information that we can look at. First of all, we can look at the root mean square error of approximation. That's the RMSEA that we looked at just a few minutes ago on that previous screen. It's 0.049, which is less than 0.05. So that would be good evidence of close fit to the data. Then we also have, when we look again at the, let's see if we can find it here. We have our chi-square test. We have the maximum likelihood chi-square test. There's the 0.2853. There's also Brown's ADF chi-square, which is also not significant. So we have evidence of good fit based on the chi-square test. You can also see, too, that, let's see if we can find it here. There's some other fit statistics. You have the normed fit index and non-normed fit index. And basically with these indices right here, what you're looking for are values that are above 0.9, preferably above 0.95. So the closer to 1, the better. These basically are going to range largely between 0 and 1. You might have, I think for the non-normed, sometimes you might exceed 1, but basically you would interpret the value as 1 in that case. So you're looking for values that are close to 1, so values above 0.9 or preferably 0.95 would be considered good fit. You also have the comparative fit index, which is also another way of looking at fit here. And so you're also looking again for values that are closer to 1, and values above 0.9, preferably above 0.95, would be considered indicative of a close fitting model. So really you've got evidence right here from these 3 fit statistics, evidence of good fit. Then you also have the standardized root mean residual. And so in this particular case, you are looking for values that are less than 0.05, which would be indicative of good model fit. And indeed, you can see right here that that was the case. Just a couple of other fit statistics that you might consider are the goodness of fit index and the adjusted goodness of fit index. Again, you're looking for values that are above 0.90, preferably closer to 1. So basically what we have right here is evidence overall that our model is a pretty good fit to the data. Now if it's not a good fit to the data, then we might want to respecify the model and then test out any kind of model respecifications. But that's going to conclude this particular video illustration.